talk is going to be sort of on the other end of the scale to the previous talk. We're going to be talking about an experimental project, not yet used in production, and sort of a bit of a work ongoing, and it's entirely using machine learning. And yeah, so basically, this field is a relatively new one. There's a lot of work that people have done recently that's quite promising, and some interesting results coming out. But unlike other fields, so for instance, if you're working in image recognition, it's sort of accepted how you should model those sort of problems. You're probably going to be using a convolutional neural network somewhere in your stack. And we probably didn't quite reach that level of agreement on how do you do things yet. So we basically are going to talk through this project that we've been working on, which is sort of an interesting project in its own right, but it's also a good vehicle for us to learn about, well, how should we model code and how should we tackle these sort of problems. So, things like how do we deal with strings, but also how do we gather data, right? We're dealing with the supervised learning system, so we've got to have some data to learn from at the beginning. And, other issues that we're not going to touch on is sort of how do you deal with sparse labels. So for example, if you're building a bug detection system, probably your labeled examples are mostly not going to be bugs, I guess, depending on where you get your data from. And also where should you apply this kind of a tool? If it's not exactly the same as the tools that people have got more experience dealing with, where should it go? So we picked this problem of probabilistic type inference, basically, because we think it's a good sample problem to learn about how do we do this sort of thing. Our reasoning there is basically classification is easier than generation, which would be the other natural thing people want to look at. But with generation, if you're doing machine translation or something like this, it's sort of quite tough to know whether you've done a good job or not. Whereas with classification, you can say, okay, we have accuracy, we have, F1 scores, things like this that we can understand. And so if we're going to keep our problem simple because we want to work out, are we doing a good job in this modeling game, that's going to be a useful property. We also don't have to deal with sparse labels. So types are roughly evenly distributed, and they're also dense within the source code. But yeah, it's also got the potential to be a useful tool, particularly for dynamic languages. A lot of code has been written in JavaScript and Python and things like this, and people are sort of coming around to the idea that actually maybe static types are a pretty useful thing, and there are these gradual typing systems that people have tried to bolt onto the top of the language. But it doesn't necessarily work as well as you might want. And there's a lot of friction in converting an existing code base, for example. So we're going to focus on JavaScript. We could easily have instead looked at Python, would have made sense as well. But JavaScript's a very widely used language, and sort of that use is increasing, front-end web apps, these sort of things. But also on the back end, Node.js is very popular. And it's hard to statically analyze. Which is not to say people haven't done work in this area, but it's not an easy task. And yeah, there are a couple of these competing gradual typing systems that people have tried to add to JavaScript. So FlowType and TypeScript are probably the best known. There's the quote here that sort of illustrates a little bit maybe why this is a hard task, because you're trying to sort of retrofit this abstraction onto a language that wasn't designed for it. So you're going to have to make some compromises somewhere. And we sort of think that, well, maybe probabilistic typing is actually quite a good way to deal with this. Yeah. And so also I mentioned this conversion problem. So it's sort of known that in industry people, Airbnb, for example, tried to move towards using Flow, and they found that actually this conversion wasn't as frictionless as they might want it to be. So just to sort of, I don't know how familiar people are with JavaScript, but it has some pretty counterintuitive behavior. There are some examples here from a talk that I can recommend people go and watch if they're interested. The link's down there at the bottom. But basically, you have these behaviors which, of course, if you understand the spec in great detail, obviously that's what happens. But as a programmer, it's not necessarily that obvious that that's what's going on. So in this first line, you're adding an empty array to an empty object, and you get the string of an array with one element, which is object. But if you just reverse the order, you get 0. Which, I'm sure if you are a JavaScript guru, that's completely obvious that's what should happen. But if you're me, that's not necessarily the case. And then also, more confusingly, you wrap that into brackets, the behavior goes away. So that's sort of a difficulty if you're a programmer, but it's also a difficulty if you're trying to build a system to reason about this sort of language. And TypeScript, they made a conscious decision, actually, that they weren't going to insist on soundness, basically because you wouldn't be able to use most realistic JavaScript code. So I guess the point I want to make is that this is even if it's deterministic behavior, it's pretty counterintuitive. And maybe, yeah, these probabilistic types could be a good way of reasoning about a system that has this slightly odd behavior. So yeah, summary. JavaScript, widely used, can be hard to understand. There are relatively few tools to help you understand it, and this probabilistic typing could be a good way to approach that. And of course, many of the issues that JavaScript faces do apply pretty well to other languages. So as a vehicle for learning about this, it's a good choice. So if you want to start doing some deep learning specifically, but machine learning in general on source code, there are a couple of ways you could go about doing it. And the most obvious, I guess, if you've taken an intro to machine learning course is, well, I'm just going to treat this as a linear token stream. And it sort of has some intuitive sense because that's kind of how a human programmer reads code. You sort of go backwards and forwards looking at things. And so maybe a recurrent neural network or something like this that's just dealing on these linear stream of tokens could be a good way to do it. But it turns out that LSTMs and RNNs, which the point of them is that they can deal with these sort of sequential data sets and remember things and learn to do a good job at whatever task you're trying to solve, well, it turns out they don't actually work super well, especially as you have longer and longer range dependencies. And it's arguable whether code or natural language is more complicated, but I don't think it's controversial to say that long-range dependencies are more common in code than they are in natural language, right? You can define a variable somewhere and then it's used miles away in the source file. The other weakness of this sort of approach would be that, well, the model has to not only learn about the semantics of the program, but it's got to pick up on the syntax somehow. So if you choose this route, you're sort of making the problem harder for yourself than maybe you have to. Yeah. So very, very contrived example, just to sort of illustrate what I mean. If we have this code here on the left, we've got some variable declared on the first line, and if we want to know anything about the result on the 9th line, we need to link those two things together. If you're going to use a linear character-based model, then you've got 117 characters between that you've got to somehow deal with and realize you've got to remember this thing 117 characters away. Obviously you could use a tokenizer or something like that and split on tokens, so it sort of reduces the burden. But if you're going to start using things like a tokenizer, you're using these tools that we already have that can do things to this language. Well, why don't we go a step further and just say, well, okay, we go straight to the AST. And so the AST would give you 7 edges, right? So that's much better than 117. The data structure we're actually going to use is this Augmented Ast, which is, yeah, you basically have a shortcut between those two things, and now there's just one step in the data, I should say. Yeah, so this Augmented Ast, it's very similar to some work done by the guys at Microsoft. So this paper from Miltos and Mark, it's got some very closely related. And there's going to be a talk tomorrow, so I can highly recommend everyone comes and watch Miltos tomorrow. But basically the idea is we take the Babylon parser, we produce this AST, so we haven't really done any work there, and then we add a load of edges to this tree. And those edges, basically we just sat down for a day and we thought, okay, well, deep learning, we just throw all of the stuff we can think of at it. So we just tried to come up with things that we can statically define. We spent, a day or so trying to just think, well, what could we add? And we sort of trust that the model's going to have some way to reason about this stuff. So in the end, that ended up being something like 96 kinds of edges, and they're things like, various relative positions in the tree or the linear token stream, or shortcuts between return types and throw statements, things like this. But more importantly, we've got these data flow edges. So I'm going to talk about those in a bit more detail because we've realized they're pretty important. So data flow is the term used by Miltos in the previous work. It's not exactly the same as that, but it's very much in the same line of thinking. So this is then what you actually get in this sort of very contrived example that I previously showed. This is what that looks like in our Augmented Ast. So obviously I'm not expecting that people can understand what this really means, but the important point is that we've got these sort of nodes here, which are the return type, the result of our using the variable we've declared here. And there's, the main thing to notice is that there's not that much distance between them, whereas all of this stuff is the sort of superfluous padding that doesn't really do anything, and we definitely don't care about when we're reasoning about what's going on here. And the other thing to note is that we do have these intermediate nodes, right? So if you're dealing with a linear token stream, maybe you don't have this sort of intermediate values that you can reason about. Now we're doing this supervised learning, so we need a data set to work from, and it doesn't, we're not like image recognition. There isn't just a big data set that we go to. So we had the idea of cloning repositories from GitHub, basically. So we take a huge number of JavaScript repositories, and we clone those. We then try and add tracing functions to the code base. So if that piece of code is run, then we get to know what the runtime type was at the point that it was run. And then we find some heuristics to install dependencies and some other heuristics to then run those tests. And then when the test is run, wherever the test touches, we get runtime information about that bit of the code. And we're only considering these basic types and primitives. Basically, we're trying to make this task easy for ourselves because it's a sort of a learning experience. So we just stick with that for now. Yeah, and we get something like 110 repositories. We've split by repository to make it a sort of fair test of the real world. So if such a tool existed, we've trained it and we've got this trained model, we're not going to have trained on your organization's code base necessarily. Yeah, and then do the split. Yeah.
So now every time I see data sets cloned from GitHub, I have to remember this déjà vu paper that showed that almost no JavaScript files on GitHub are actually unique.
Yep.
So that I think 94% of all files are clones.
Yep.
So that did you consider this for?
Yeah, we've removed clones from this data set.
Okay.
Yep. But in principle, if you're doing deep learning, maybe you don't actually have to care about this.
Well, if you have overlap between train and
no, it's true. It's true.
Yes.
Well, I'll come to that point a bit later. Actually, yeah, you definitely do need to consider that.
So running the code to get the types is pretty involved. Did you consider using existing type annotations, so code that has been annotated?
Yeah, so we wanted to have two things to consider. Firstly, this is a sample project to learn about deep learning, but it's also a sample project to learn about, well, how would we build a tool like this, right? So if we've gone and used some nice data set of JavaScript code, but we've now okay, we want to run this on Python, and there is no data set, we haven't solved that half of the problem. Whereas if we're doing this actually translates very naturally to any language, right? Assuming there's sufficient examples on GitHub. And I should also say, so we ended up with these 810 repositories. We had far more than this. We could have gone up to, I think, 20,000, something like this. We actually found this is like a sort of good balance between the two. So yeah, I guess that's the reasoning. So the goals for the model, it sort of relates a little bit to the talk Earl gave earlier. We want to deal with structure, the algorithmic side of things, what the program's doing, but also we want to deal with strings, which are what the programmer or the person writing the code is thinking about alongside the structure. And ideally, we'd like the model to be explainable, which is, these are deep learning systems. One of the weaknesses people are aware of is where you don't really know what's going on necessarily. And as an example of what the model actually produces, just a bit of a spoiler, this is the sort of thing we get, right? So we have a function and we can infer, we sort of used these flow types just to try and let people know what's going on. And by hovering over this length argument, we can see, well, okay, this is where the model seems to be paying attention to. So it's, pays attention to some areas where length is used more than others. Arguably we need to work a bit on the visualization. But yeah. So we have these two kinds of information. We've got the node level information. So we've got the abstract syntax tree node type. We've got strings. We might have properties that correspond to that node type, something like this. We also got the structural information, which is pretty much how they're connected and what kinds of edges connect those nodes. And when you're dealing with deep learning, you're just assuming everything's a vector somehow, and we're going to find a good way to make those vectors and then find a good way to combine them, and then perform classification over that at the end. And so to talk about this initial node representation, so this is like the starting point that we have in this kind of a model. We do a character level convolution of strings to produce some encoding vector. So this is quite a standard technique in natural language processing if you're familiar with it. We chose character level convolution rather than a recurrent neural network, something like that, basically because it's faster and it doesn't really seem to change the performance. And so the approach is that we take all of the string information in the data set, we truncate it to 30 characters and pad it if it's shorter than 30 characters, and then feed it through this thing and we get a vector at the end. We also have a sort of a binary vector of node properties. So yeah, these are, if you've got a binary expression, maybe you've got different kinds of equality in that binary expression. And we also have the node type itself. So we do an embedding, very much like a word embedding on the type of the node in the AST. then concatenate all those things together and feed them through some linear layer. So we end up with a vector of some size that's basically the size of that is a hyperparameter that we can mess with. So we then use this graph neural network type model. So these are pretty recent, well, relatively recent kind of model in the deep learning community, but they've had quite a lot of success in the sort of short time they've been around and spawned a variety of different approaches. They can all pretty much be explained in terms of this idea of message passing. So there's a good review from Gilmer et al. There that I can suggest anyone reads who's interested about this. But basically the idea is you've got these vectors for each of your nodes, which you've computed in some way, and you're going to pass them around somehow, and hopefully the way you learn to pass them around is a good one for the task you're trying to solve. So just to try and illustrate this thing here, say we've got these different nodes and they've got vectors corresponding to their color. If we focus on the centermost node, we use the connections in our graph basically to pass those around somehow, and we end up with a new vector. Yeah. This is like a schematic of the model we're using. It's sort of similar to a number of models, got like similarities in the various components we're using. Basically, we've got this attentional message passing, which is just one kind of model that you can use for doing this kind of message passing graph convolutional step. We have, if you've read this paper, there's basically like these different attention models. We have a separate attention model for the union of all of the edge types apart from the data flow edges, and then the data flow edges get a separate attention mechanism. So we get vectors corresponding to each of those, and then combine them and feed it into a gating mechanism. So the gating mechanism is exactly the same as you'd have in a recurrent neural network, and the reasoning for this is pretty much that it allows your model to go deep. So if you're dealing with a sort of vanilla graph convolutional method, it's sort of known that they're quite hard to train as you add layers. So if we want to talk about performance, we actually get a performance of 90.9% accuracy, and it doesn't seem to be very sensitive to random seeds. So we rerun the training process 10 times and then test it on the same test set, and there's a swing of plus or minus 0.2% was the biggest. So it's pretty stable. But we don't necessarily know from that, is that a good result or not? So if we're going to guess and just follow the data distribution, we'd be looking at 32% accuracy. So we just choose the most likely class. So we have to at least have done better than that, or we're not really doing anything. If we take a baseline model, so we took a model where we only consider the information that a single node could know about. So we have the string, we have the abstract syntax tree, node type, and the properties and so on. But we also concatenate the incoming and outgoing edges as a binary vector. So if I happen to have like a next traversal edge, I get a 1 in this vector. And then just feed that into a feed-forward network. So that gets us a performance of about 67%. It's not really easy to do a fair comparison with any other system. There are other systems, of course, doing probabilistic type inference. And there's a really good paper from 2015 that has approached the same problem using probabilistic graphical models. They're using a different data set, though, and so this data set doesn't have the tests that we need to feed it into our system, so it's difficult to do this fair comparison. But so in this paper, this Ratio et al. Paper from 2015, they get an accuracy of 81.6%, and so they're a bit more sensible about how they do their prediction. They don't predict on everything; they just predict where they're a bit more confident. So I think they don't choose a type 35% of the time. But just to give some idea of where do we fall on how these tools can perform, we seem to be somewhere around better than this. Now, when you're trying to judge a system like this, you've got to, deep learning, not so easy to understand what's going on. So you've got to sort of try and do a bit of science on the model after the fact to work out, what is going on. So what we've done here is broken the data down by the node type and the class, and then we've measured the accuracy for that combination. So we've got, an identifier node and an object, and how often are we correct. So what we don't want to see is just like a line going from the bottom left corner to the top right corner, which would suggest, we're very heavily dependent on the amount of data we've got. We're not really learning anything particularly, we're just sort of learning to mimic the data in a useful way. But that's actually not what we see. So we see that we've got this, we do relatively well, even when we've got quite a few examples. But if we have many, we're also doing pretty well. So there doesn't appear to be some strong dependency on the data, which is a good property for us to have. So here's an example of the model, basically where it doesn't get it right. So the answer is wrong, but I think this is sort of a very interesting point, and it sort of harks back to what Earl was talking about earlier. So on the right-hand side, we've defined constant h, which is an array, and on line 5, of course, the model has correctly inferred that h is an array, which is not necessarily a very impressive task. But on line 5, we've then checked if the length of that array is greater than 0, and so we, as people who write code, know, well, that's a Boolean. And indeed, the model has learned, okay, well, that's a Boolean. But on line 8, we've chosen to use a different variable name, so we decided to call it size. And the model now incorrectly decides that the size variable there is a number. Now, of course, we're dealing with this AST, so we can sort of look at our prediction per node. And we find that the right-hand side is correctly a Boolean, as you'd expect. But this use of the word size has sort of overwhelmed the model and made it predict that this is a number. So, I mean, depends who you are to say, well, which way around, what is the right answer here? If you're a sort of a traditional person working on some static systems, then, well, clearly this should be a Boolean. What are you talking about? But if you're someone who's written codes, well, we all know size probably is going to be a number. And so there's some sort of mismatch here, which is a sort of a, I don't know of many tools that would allow you to reason about this sort of thing, and perhaps it's like an interesting avenue to explore. Yeah. So I talked also about this data requirement before. We only have these 810 repositories, which may not sound like a big number, especially if you're familiar with deep learning systems and the millions and millions of examples that people use in ImageNet and things like this. But we wanted to see, well, how are we going to benefit from increasing the dataset size? And so that's basically what we've done here is kept the same test set, and we've just chopped our training set, into different sized amounts. And then we perform the full training as we would as usual, using our best hyperparameters and so on that data set, and we evaluate it and just see, well, how does it affect the performance? And this is sort of exactly the shape of graph you want to see. It means that you're very close to the optimal performance. It's just if you're looking at this for more traditional tasks in machine learning, your x-axis would just be, it would have some extra zeros added to the end of it. You'll be talking about millions. And that's kind of an interesting question, or an interesting thing to observe, because if it is known that these deep learning systems require huge amounts of data, well, why don't we require huge amounts of data here? Is it just a particularly easy task we've chosen? Is it that there's a sufficient exposure to the different patterns we need to learn in our training set? Or is it that the model somehow has a good inductive bias that allows it to overcome the limitations in data? But yeah, you can basically see we peak at around 4,000 files, which is really not so many. So to try and understand a bit more why that might be the case, we perform an ablation study. So this is a standard thing in deep learning where you basically take your model and you delete bits of it and just see, well, how does that change the performance? So if we don't have our separate edges for the data flow, we just instead have the union of all of those edges, the performance drops by about 5%. And if we remove the strings, so I should say these are not sort of consecutively removing things, they're separately removing things. So we have the data flow edges as usual and then remove strings. It drops down to about 77%, which sort of suggests our idea that maybe this is reasoning about language in some way is probably correct. So it's interesting though, if you remove the data flow edges completely, so you have all of the other edges we consider, it drops down to 53%, which is not that good. And indeed, if you remove all of the edges, it's around the same performance. And if you only use the data flow edges, it's around the same performance. And this actually makes complete sense if you think about how these models work. There's an idea in image processing, which you may or may not be familiar with, which is the receptive field. So if you have, you're trying to classify the pixels that correspond to someone's face or something like this, you might need to have information about, I don't know, a nose or something. And your model is going to be constrained on how far that information can propagate, basically by how deep you've stacked your layers. We have exactly the same thing happening here with these graph neural networks. So on the left here, we've got these sort of lighter red nodes, and this center node, we're talking about the update. And so in the first layer, it can only consider information from its immediate neighbors. And in the second layer, obviously that goes out one step further, although there's this interesting property where those further away neighbors haven't been through the same number of, transformations by the network itself. But the important thing is it's completely impossible for this centermost node to know anything about these nodes here, other than, I don't know, any sort of overarching statistical patterns it's picked up about how things tend to be used. And so if basically my feeling is that if we have removed those data flow edges, we're making our task to propagate information much harder. We're going to have to take many more steps for the information to propagate. And if we only have the data flow edges, well, the information propagates perfectly between them, but you can't then learn anything else about the structure of the program. And so we formed a sort of an experiment to see, well, how does that depth affect our performance? So we can vary the number of steps, message passing steps, or layers, or however you want to think about it, that the model is considering. And its peak's actually around 4 steps, but even after 2, it actually gets pretty close to the peak performance. And that's sort of surprising, right? The reason we added the gating to our model was that, well, we wanted to be able to have very many layers, because, that would sort of intuitively make some sense if you're going to be passing this information around. But that doesn't seem to matter so much, for this problem at least. And so to sort of illustrate that a little bit more, we've got these 2 graphs here, which are maybe slightly difficult to interpret, but basically we've got on the left, we've got a histogram of the mean shortest path in our source file. So we take a source file, get the graph representation, and we take all of the pairs of nodes, and we measure the shortest path between them. Then just the average of that, we get a value for each graph. And this is the histogram of that. So if we have only the AST, then that's naturally shifted to the right. If we add our shortcut data flow edges, then it's shifted to the left. But the average of that is still pretty high, right? It's like 6 still, and we're finding that even after 2 steps, we're getting pretty good performance. But if you look on this chart on the right, this sort of gets to the bottom of what might be going on. So what we've done here is we've taken, again in our graphs, we look at all of the pairs of nodes that do have a data flow edge between them. Then we look at what's the shortest path between them if we delete all the data flow edges. You can actually see that's pretty long. It's more like 8 steps, something like this. So that's sort of suggesting that if we didn't have these data flow edges, we'd have to have at least 8 steps for information to propagate between these 2 things on average. And the models are known to be harder to train the deeper they get. So it's arguable, it's an experiment we should run to just see, well, if we've removed them, we make the model deeper, how well does it do? But yeah, it's sort of an interesting point to think about. So we performed one other experiment, which is basically this idea of fine-tuning. So I said we split by repository at the beginning because we want to be as fair as possible to the real world. We don't necessarily get to see people's code before we run on it. But what if we do? And we can test that by basically abusing the test set. So you've got to be a bit careful, and maybe there's more work we need to do here. But the idea is we take our test set and we split each of the repositories in the test set in half. We train on one half and then evaluate on that other half. And we see how does the performance change if we do this fine-tuning. So fine-tuning also is a relatively standard machine learning technique used in image processing, where you take a pre-trained model and then on your specific problem you retrain it a little bit, but you don't let it change too much. So we do that, and we find that we actually get an improvement in performance of around 4% in accuracy, which is quite high when you're getting up into the 90s. Surprisingly high, in my opinion. It does suggest that we were quite right to not allow the split between repositories when we're doing the training, and also to make sure we've removed clones, because it appears that it does make a big difference in terms of performance. But yeah. So just as a summary, our performance looks like this. If we're just guessing, okay, well, unsurprisingly, that's not a very good result. And we remove various parts of the model, performance decreases. But this performance up at the top there is well, it is sort of a question, like how good is that? Say we have an accuracy of around 91%. Well, is that good? Okay, so if you can imagine you're a programmer, if you're writing Java or something with static types, if you imagine 9% of those types were wrong, that's not so useful. However, the way we can use this is sort of interesting, right? Even if we ignore the fact we could do some kind of interesting reasoning about strings as well as structure, we could incorporate this into some sort of existing static system. Maybe we could have like a bit of a dialogue, for example, with flow, where we sort of build up, ask questions, we're unsure about what's going on here, and maybe we can sort of build up different bits of functions that we have confidence that we can add these types to. There's also, the possibility we could add in types that we are sure about. So for example, maybe we could run some runtime analysis, and then we get to know, oh, well, okay, well, this one actually is a Boolean, and how does that change our inference if we get that knowledge? That'd be a very natural thing to incorporate into this sort of training. But yeah, the question is, well, how do you combine this sort of thing with formal methods? I mean, is it a useful thing to do? And if it is, what's the right way to do it? And these are definitely things we're going to be exploring, and if anyone has any ideas, definitely like to hear from them. Yeah, so some takeaways. We've ended up with this 90+% accuracy in type inference for JavaScript. We surprisingly don't need that much data. And how we represent that data actually does matter quite a lot. Also, strings are important. And yeah, the disagreement we get when we're looking at strings and when we're just looking at structure might be an interesting thing to consider. We do actually have a demo of this at this URL here, if anyone wants to have a look at it and try and work out what's going on. And definitely come and ask us if you've got any questions. And similarly, if you're interested in building these sorts of models, you should also definitely come and speak to me afterwards. So there are a few people here from Proto to date. Samir and Nora are back in the office, but if you want to speak to anyone, come and find us. And yeah, any questions? Yep.
So if I can see from a diagram, it basically sees that you are using hard attention after the graph neural network.
Well, it's, yeah.
Have you tried using attention after the guru left?
We actually haven't, no. I mean, so obviously that's a bit of a trend in a lot of areas of deep learning, just throw attention everywhere. And that's sort of, it's definitely something we're looking at in a variety of places, but we haven't tried that yet. This is definitely ongoing work.
It's just a complicated combination of all the nodes here which you are currently using.
Yep.
But if you see the machine translation history or the
Yep.
literature on that, it shows that group captures much better information and the shared representation as compared to the graph neural network. And at the same time,
So in translation, though, you'll... Sorry.
Confusion matrix regarding...
Yeah, I do. I can show you afterwards if you're interested. Yep.
Okay, so do you have a rough figure that what was the false positive in it?
Oh, I'd have to check. It obviously varies per... So the interesting thing for us to look at is, is it per node type? Like, because there are certain nodes that are far more common than others. And obviously there are some nodes that can only have one type, so we've excluded them for all of the measurements we've got here. I can't remember what exactly it is. But our F1 scores are unsurprisingly around the same as our accuracy.
Yeah, one of the questions, like the way you described the reasoning which you're doing in your model.
Reasoning is a loaded word.
Looks like a membrane network would be much more beneficial.
Like a what, sorry?
A membrane network.
A memory network. Yeah, that could be. I mean, this is definitely ongoing work, right?
Just consider the internal state there, there's the internal memory for that.
So,
but
yeah.
Membrane network, you have a multiple hop over that.
Mm-hmm, mm-hmm.
So multiple hop itself represents hard attention, but
Yep.
you have multiple iteration over the data. So since you're targeting with a certain time step,
Yep.
that can be a beneficial.
Well, time steps are also a bit misleading, right? What we'd really want is just somehow, one thing you could do is, okay, well, we're going to forget all this structure, we'll connect every node to every other node, and our model's just going to learn perfectly what it should do, right? So the time steps are sort of misleading. It's not time steps in the same sense as time steps when you're looking at a sequence of tokens, right? Like it's a different thing. It's just like an unfortunate limitation of this kind of model that you have to propagate information somehow. It's much more similar in my mind to convolutional nets on images than it is to sequences. But yeah, these sorts of things are definitely things we want to look at. This is not complete work necessarily. Yep.
Have you tried visualizing the weights of the attention?
Well, so if you remember this picture that I briefly showed, this is our attempt at doing so. So this is not perfect yet, but it's clearly what the model is doing. So we can't really argue with it on that sense. Clearly, so it's.
So maybe could you explain what we're seeing?
Well, I can explain what we've shown, but what we're seeing is up to the model, I guess. So basically, we've got our, so the thing the model's inferred, we've got these flow types, so colon, then some type. That's what the model's decided on. If we're hovering over the len argument here, which is decided as a number, the sort of opacity of the thing we're looking at, the tokens in the function, correspond to the attention that the model's given to those different nodes. So you can see, okay, well, pads here, it doesn't seem to care about very much, and it doesn't really seem to care about here, but it does care about string here. So it's not that easy to know how do you, especially when you've got these multiple, because there's multiple layers of attention here, right? So how should you propagate that information? We don't have a good answer yet, and I sort of suspect it's going to be, you know, a bit of a matter of working out what the visualization should look like. But the interesting thing is that it definitely does seem to care about this 10. So it's decided this is a number. This 10 is somehow important, right? Which is kind of nice, and it's the first steps down the path that you might want to take to having some explainability in these sorts of models. Yeah.
I'm just wondering if you look at, take a histogram over the steps of inference and type judgments to infer the type.
Sorry, what do you mean?
So when you infer types of in a program, you go through several series of steps of inference.
We don't.
No,
in this system. Yeah, no. No, sure.
Is that number 4?
Well, that'd be interesting to know. I don't know. But it's more than 4, it'd be 2, right? Like, because if you look at this, where is it? This graph here, okay, 4 is our peak, but it's a pretty minor peak. 2 is, like 2, it's pretty close. Like 1 is not good enough. So I don't know if that number is 2 or 4 or what.
So the related point is, I've seen a lot of people showing this connectedness in JavaScript, right?
Yeah.
Now the thing is, like, I was teaching streams this quarter, my students last quarter, and like they really struggle with collectors and streams. It's all very nice and beautifully defined and all this, but it's still hard to understand, right?
Yeah, definitely.
So I really wonder whether the occurrence of these terrible things in JavaScript is just as rare as
well, okay.
Maybe they just never happened. We like to look at
maybe,
this,
but
type people nightmares.
It could be. It could be.
It doesn't matter.
Well, I guess then. So I don't know how much code you've read of other scientists who've implemented various methods and then released them into the wild. Obviously, the code you've written is perfect, but I think if you look around, even these very smart PhD developers, you find that code, well, is sort of arguably good quality. JavaScript, I think there's a much wider range of people using the language. I've seen some pretty horrific JavaScript. If you ever, just for fun, inspect a website, look at what is actually running there, and assuming it's not minified, the code quality is variable, I think.
But is it the kind of thing that would confuse type inference? Really bad type stuff?
Maybe. It's possible. I mean, this is the strength and the weakness of this kind of approach. We don't really know what it's doing, but at the same time, you can't really argue with the result it's getting because we've been sort of scientific about what we're doing. It's definitely an interesting question, something to look at. Yep. Oh, sorry, yep.
Have you shown these results, these predictions to users, and how useful have they found them?
Not yet, and don't know. My feeling is that this sort of model, you're never just going to run this. Maybe if you're like exploring this idea of strings, maybe it's enough to say, well, this string looks weird, and we can give you some intuition about why. But if you were trying to do some like flow conversion, something like that, my feeling is you need to have a static system alongside this, and that's really where the strength of this approach is going to be. These languages where you can't reason about stuff in a sort of concrete way that you'd like to, maybe if you guide it with this probabilistic stuff, that's actually an interesting avenue to pursue. Yep.
Actually, I was just curious, you mentioned in the beginning that these LSTM models, sequence models have these long-term dependency problems. So
yep.
What kind of performance do they get on these?
Yeah, interesting question. So this is something that I haven't actually done. Basically, there's a natural way to approach this, which is pretty much to copy a named entity recognition type model. So named entity recognition is you've got language and you want to identify company names or something like that, and you operate on a linear token stream. So you could have something like that operates on this. You'd have a bit of an issue because you'd have to have separate classifiers because you have these sort of nested types, particularly if you wanted to consider intermediate nodes, for example, so like the result of an expression, things like this. It might not fit so naturally. I think, yeah, this is clearly a comparison that should be done. I don't have an answer for you how good it would be. Yep.
So just a quick, maybe a follow-up to this last one.
Mm-hmm.
How easy would it be to extend your approach to infer kind of union types and intersections?
It seems doable, but as soon as you get to, it's doable, but you might have to look into something like reinforcement learning or something like this to combine the bits you've got. There may be a way to do it, just assuming that there are potentially this many union types, and then you're looking at vectors that correspond to that within the file or something like this, but it wouldn't be as natural a fit, but it's definitely something that can be tackled.
Yeah, I guess I was wondering whether it would capture some of these, do a lot of these strange JavaScript idioms fall into that pattern.
Yep. Yeah, could be. Yep. Oh, sorry.
I actually thought, because we've hit time now, so I thought maybe we break up the discussion now and take this out into the lunch break. And I think tomorrow we'll have another talk in very much the same vein, and so we can continue the discussion about graph models there. So maybe let's thank the speakers in this session again.